Hello and welcome to my lecture series over different type of radiological topics. Some are for the specialists, some are for the students, those who have taken radiology as their career. There are also lectures for the technicians and medical imaging technology boys. Now this time the lecture is on basic physics, and that is also what is the ultrasound physics behind transducers. This topic will be covered in short in this lecture. If you want to have extensive detailed information about same topic, you can go to my website or you can go to my YouTube channel. You will get ample of detailed informative lectures on that. Now to start with the disclosure. Most of the material we are used here is from our departmental day-to-day teaching purposes. Some may be downloaded from the web, which is royalty free. We acknowledge with thanks for those. Now with that brief introduction, we are starting our lecture on ultrasound physics pertaining to the physics behind transducer designs. Now let's come to the detail. What is a transducer? The transducer is a device which a ultrasound or ultrasonographer, ultrasound doctor holds in his hand and keeps it on patient's organ of interest for study. But there is a lot of physics involved behind designing of this transducer, which we are going to see in this lecture. The transducer consists of number of piezoelectrical crystals which are arranged inside the core of the transducer. Now, these have the ability to vibrate and produce a sound wave of a particular frequency when electricity is passed to them. The same transducer are capable of receiving reflected echoes of the sound waves. Now, from these waves received, sound electrical signals are produced. Now let me make it a little bit simpler. Piezoelectric phenomenon is the phenomena when electricity is applied to a crystal, it expands and contracts, or in other words, it vibrates. Due to this vibration, it produces a ultrasound. Now once this ultrasound comes back, it hits the crystal again, and in this process it sets it again into vibration, where this sound energy is converted into the electricity. Now this electricity or these electrical signals which are produced at the piezoelectric effect are equivalent to the sound waves which are coming back. So brighter signals are produced by the sound waves which are coming in more number, and that is what is happening in the transducer, and extensively these topics are covered in some other lectures. Now let us come to the characters or physics of transducer. The first is a duty factor. What is duty factor? The most models of the ultrasound operation, only 1% of time is spent in gathering a pulse of an ultrasound wave, and 99% of the time is spent listening for these echoes. So in other words, when a transducer produces the ultrasound waves, maybe they are 1%, and spends more time in gathering whatever is coming back. So this is called as a duty factor, which is 1% in such cases. Now transducer pulse repetition frequency, PRF, that is routinely called. PRF, it's a number of pulses, send and listen cycles of the ultrasound sent by the transducer per second. So that is PRF, and it is dependent on the velocity of the sound and depth of the tissue being interrogated. The deeper the tissue is being examined, the longer the transducer has to wait for echoes to come back, hence lower is the PRF. Now we'll go to the beam. Ultrasound frequencies ranges from 2 MHz to approximately 15 MHz. We are talking of the beam properties. Now although even higher frequencies may be used in some situation, the ultrasound beam is focused by a transducer so as to be as closer to a flat plane as possible. and the beam is made up of 10 to thousands of scans lines. Now, ultrasound beam is important when a transducer is designed, because sometimes we need a cone-shaped beam and sometimes we need in a straight line. Now, transducer and identification marker for the side. A sonographer is doing ultrasound, a screen is projecting, but the side of the sonographer on the probe has got a marker, as well as on the screen, same marker has got an identity on the screen. So we know which is right side, we should know which is medial side, and we should know which is the lateral side. So there is always or usually a dot, groove or light on the end of the transducer for assessment of orientation. In corresponding making is also displayed on the screen to help an orientation of the images. So the light on the transducer and a marker on the screen gives us a perfect orientation. Now, resolution in ultrasound, it is the most important factor. There are different type of resolution. A is axial, B is a temporal, and C is a lateral resolution. Let's see them one after another. The transducer resolution could be axial. Now let's go into it. It's the ability to resolve object in the line of the ultrasound beam. So it discriminates between the two nearest objects. That is the axial resolution. Now, factors affecting axial resolution include spatial, pulse length, and frequency. Now, second type of resolution is a temporal resolution, which refers to the ability of detecting moving object in a field of view in their true sequence. Now, the number of frames generated per second, that is called as also frame rate, determines the temporal resolution. So it is important when the objects are moving which you are sonographing. Now the third is lateral resolution. What is lateral resolution? Resolution at 90 degrees to the direction of the beam. Factor affecting lateral resolutions are distance from the transducer, it affects the resolution, the side and grating lobe levels, then the width of the beam and frequency. These are the things which decides it. And now we'll see how the ultrasound is produced and detected. Here we are not going into details of piezoelectric effect. Here we are going only into the details of the transducer. The transducer has a electric cable which uses a supply and takes signal from it, and it has got an array of piezoelectric crystals. These are the two main important things, which has got many supporting things like the plastic nose, then acoustic insulators, then backing blocks and metal outer coverings. These are all protective, but the most important here is piezoelectric crystal array, or what they are arranged. They are most important. We are theoretically seen how ultrasound system works. Now we will see how the transducer are designed and what are the preliminaries. First, it should set a crystal to vibrate. So it should have a line or row of crystal which can be set into vibration, resulting into emission of sound waves of desired frequency. And it should also be capable of converting back sound waves received into the electric signals. So whatever signal it will receive back, they are transferred by means of an electrical signal. Now these are the transducer. It converts electric energy into the mechanical energy and serves the same function, that is the opposite way. When the electric supply is applied to the piezoelectric crystal, it vibrates. It gives ultrasound. When it receives ultrasound, that sets it into vibration and a signal is produced. Now, what are the functions of transducer? Here I have shown you is a transducer. Now see, you can follow the cursor. Transducer is sending ultrasound waves. Now this is the object. Now object is sending some waves back. and this is a transducer which is receiving it again. So this is what is happening, and a signal will be produced. So transducer converts electric energy provided by the transducer to the acoustic pulses directed to the body, and also serves as a receiver of the reflected echoes and converts acoustic energy to electrical impulses or processing. This is on the principle of piezoelectric effect. Now, what is the bandwidth and band technology? This is a technology used by modern USG machines. Shorter the USG pulse, greater the bandwidth. By using this principle, different range of transducer can be manufactured and can be applied at different pathologies, different organs, and different areas. Now, transducer selection, you see there is a galaxy or row of transducers. Now, it depends on what depth you want to scan. Number 2, whether you need a linear surface or you need a convex surface. Convex surface will give you a fan-shaped beam where you can scan more organs. The linear will give you straight. Now, there are transducer with small footprint. There are transducer with small size which can be used for intracavitary purpose. So there are different transducer, different wavelength, different type of resolutions, and different type of fan beams. As per the application, they are changed and used. Now, on that basis, we select the transducer. The superficial vessels and organs which are lying within 1 to 3 cm of the surface, such as breast, thyroid, testes, etc., imaging frequencies between 7.5 to 15 MHz. So high frequency probes are used because they can give a better resolution at lesser depth. For deeper structure like abdomen, pelvis, we use a transducer at a frequency of 2.25 to 3.5 when the depth is more than 15 centimeters. These has got good penetration, good surface coverage, but not as good resolution. Now here you are seeing how the ultrasound waves get propagated in a fan shape, but that depends on your selection of transducer. Now here receiver and a sender, that image acquired by receiving these echoes or sound waves coming back to the transducer, and that is what is receiver. Receiver has got same basic principle piezoelectric, that of converting this sound energy into the electric energy, and then these all signals will be fed to the monitor. So transducer itself acts as receiver. Returning echoes strike the transducer. Minute voltages are produced across the piezoelectric crystals. Then these received waves or signals are fed to the amplifier and then to the monitor. Another function of the receiver is to compress of the wide range of amplitudes, returning to the transducer into a range that can be displayed as an image to the user. The ratio of the highest to the lowest amplitude that can be displayed may be expressed decibels and is referred to as a dynamic range. Now, though the amplifiers used in an ultrasound machine are capable of handling high resolution voltage, grayscale displays are limited to display a signal intensity range of 135 to 40 decibel. There is a limit what the shades of gray and white I can appreciate. Now, depending on that, there are steps 32, 64, 128 or more than that. Depending on the manufacturer, depending on the machine capacity, these are displayed. Now, compression and ramping of the data are required to adapt the dynamic range of backscattered signals intensity into a dynamic range of images. So this all is done by the computers. Now compression is performed in the receiver by selective amplification of weaker signals. In this lecture, we have seen briefly how the transducer are designed, what are the types of transducer and how they function. In case of you want detail, please visit our website or our YouTube channel. I thank you for giving me your valuable time. Please do visit our website for comprehensive and detailed lecture over these topics and many more. Thank you, goodbye and take care.